Welcome to part 3 of our Applied Chemistry series, where we'll be exploring solid fuels. Solid fuels, especially coal, play a crucial role in energy production, particularly in industries like power generation and metallurgy. This section covers the proximate and ultimate analysis of coal, the differences between high and low temperature carbonization, and the manufacture of coke using the Otto Hoffmann oven. These processes help maximize fuel efficiency and reduce environmental impact. Coal analysis is critical in determining the quality and suitability of coal for different applications. There are two key types of analysis: proximate analysis and ultimate analysis. Let's take a closer look at the proximate analysis of coal. This method gives us a quick breakdown of coal's components. Moisture content. High moisture content reduces the fuel's calorific value and adds unnecessary weight, increasing transportation costs. Volatile matter, substances released when coal is heated, including gases like methane, hydrogen, and tar. Coal with high volatile matter ignites easily and burns quickly. Fixed carbon. The main combustible part that remains after volatile matter is driven off. It provides most of the heat energy during combustion. Ash content. The non-combustible residue left after combustion. High ash content lowers the fuel's calorific value and can cause problems like clinker formation and equipment corrosion. So, proximate analysis parameters are moisture, volatile matter, fixed carbon, ash content. Proximate analysis helps to determine coal rank and grade. Higher fixed carbon indicates better quality coal. Assess handling and combustion properties. Volatile matter affects ease of ignition. Moisture affects energy content. Now, let's move on to the ultimate analysis, which provides a deeper understanding of coal's chemical composition. Here's what it measures. Carbon, the main element responsible for providing energy during combustion. High carbon content means higher calorific value. Hydrogen also contributes to energy production when it combusts, releasing heat and forming water. Oxygen. Higher oxygen content reduces calorific value because it dilutes the fuel. Nitrogen. While nitrogen doesn't contribute significantly to the heating value, it can form nitrogen oxides during combustion, which contribute to air pollution. Sulfur, a problematic element that leads to air pollution by forming sulfur dioxide, SO2, a major contributor to acid rain. So, ultimate analysis parameters are carbon, hydrogen, oxygen, nitrogen, and sulfur. Ultimate analysis helps to evaluate the environmental impact. High sulfur and nitrogen content lead to pollution. Estimate combustion efficiency. Carbon and hydrogen levels directly correlate with the heat output. Plan flue gas treatment systems to mitigate pollutants like sulfur dioxide and nitrogen oxides. Carbonization refers to the process of heating coal in the absence of air to produce solid carbonaceous residues, mainly coke, and gaseous byproducts. The process can be carried out at high or low temperatures, depending on the intended products. High-temperature carbonization, HTC, occurs at temperatures between 900 degrees Celsius and 1,200 degrees Celsius, mainly used for producing metallurgical coke, which is required in blast furnaces for steel production. This process yields hard, porous coke and byproducts like tar, benzene, and ammonia. Advantages of HTC. Produces high-quality coke with excellent strength and reactivity for use in the steel industry. Gaseous byproducts can be captured and used for other industrial purposes, such as chemical production. Low-temperature carbonization, LTC, happens at a lower range, around 500 degrees Celsius to 700 degrees Celsius, and is primarily used for producing soft coke or semi-coke, which is suitable for domestic use. The products contain higher volatile matter and the process is less energy-intensive compared to HTC. Advantages of LTC: produces softer, more combustible coke that can be used for domestic heating and in smaller-scale industries. The process consumes less energy compared to HTC. Coke is a porous, carbon-rich material produced by the destructive distillation of coal in the absence of air. It is primarily used in the iron and steel industry as a reducing agent in blast furnaces. The Otto Hoffmann oven is a byproduct coke oven designed to recover the valuable chemical byproducts produced during coke production, such as tar, ammonia, and benzene. This process is more efficient and environmentally friendly than traditional methods. Construction of the Otto Hoffmann oven includes chamber design. The oven consists of narrow, rectangular chambers, where coal is charged and heated externally by burning gases in flues adjacent to the chambers. Airless heating. Coal is heated to around 1,000 degrees Celsius to 1,100 degrees Celsius in the absence of air, ensuring that the coal does not burn but instead undergoes carbonization. Heat recovery. The heat generated during combustion is circulated through regenerators to maximize heat utilization, improving fuel efficiency. Byproduct recovery system. As coal is heated, volatile substances are driven off. These are passed through a recovery system to separate valuable byproducts, such as ammonia, tar, naphthalene, and benzene. This diagram illustrates the Otto Hoffmann byproduct coke oven process, where coal is heated in the absence of air to produce coke. The oven is heated using producer gas and air, with waste gases exiting the system. Hot regenerators recycle heat, improving energy efficiency. During the carbonization process, volatile byproducts are captured and separated into different compounds: tar, ammonia, naphthalene, benzene, and hydrogen sulfide, H2S. This system efficiently produces coke while recovering valuable chemicals for industrial use. Let's break down the process of coke production in the Otto Hoffmann oven. Charging. Coal is charged into the top of the oven, filling the chambers. Heating. The external flues circulate hot gases around the chambers, raising the temperature of the coal. As it decomposes, it turns into coke while volatile compounds are released. Byproduct recovery. The gases and volatile products are collected and cooled, allowing recovery of valuable chemicals like tar, ammonia, and benzene. Coke discharge. After 16 to 20 hours, the carbonization is complete and the coke is removed. The red-hot coke is then quenched with water or inert gases to cool it down. The Otto Hoffmann oven offers several advantages that make it a more efficient and environmentally friendly option for producing coke. Efficient use of heat. By recycling heat through regenerators, the oven minimizes fuel consumption, making the process more energy efficient. Byproduct recovery. This system allows for the recovery of valuable chemicals like tar, ammonia, and benzene, providing additional economic benefits. High-quality coke. The coke produced is strong and porous, making it ideal for use in blast furnaces for steel production. This quality coke is essential for maintaining the efficiency and output of industrial processes. We've reached the end of our detailed exploration of solid fuels in applied chemistry. Throughout this video, we've covered different topics. Thank you for watching, and don't forget to subscribe for more tutorials on applied chemistry and other exciting topics.